Okay, so the quantum model is our modern atomic theory. It's our modern atomic theory. And unlike the other models that we looked at, we kind of designated a single scientist to each of the models before. The quantum model is kind of like a cooperative effort from a lot of different scientists. Okay, a lot of different scientists contributed to this quantum model. So they all kind of like, this is where Bohr was kind of like our transition from old models to new models. So he was really important, even though his model didn't hold together for more complex atoms. He was our stepping stone from these old physical models to the new quantum model, which is really mathematically based. All the other models are kind of like had a physical vision that we could kind of see. And it was kind of like real concrete. The quantum model or the modern atomic model, we can't really define things specifically. It's based on probability. Okay? It's based on probability equations. So it's a little different, or a lot different, I should say, from the old ones. It's kind of gave us a new realm of physics. There's classical physics and there's quantum physics. Classical physics are laws that kind of define larger objects, like a baseball flying through the air. That kind of thing. But small particles like electrons, they don't follow classical physics because they're so tiny, they hardly have any mass, and they're moving at such high speeds that classical physics can't define it. Okay? Classical physics, like normal laws of gravity and those types of things, or the Newton's laws of motion, can't define or can't define electrons, particles as small as electrons. So there's kind of two areas of physics. This is where chemistry and physics kind of overlap. We're just going to basically look at what the quantum equations tell us, not get into the actual mathematics. Does that make sense? There's a whole lot of equations that go into defining these things. I'm not worried about all the mathematics that define that. It's really high level physics, high level mathematics. We're just looking at what those equations tell us about that. Does that make sense? About the electrons. So we're really zoning in or focusing on the electrons. So the quantum model, this is our modern day. It's all based on probability. So this is where we're going away from the Bohr model. Bohr kind of defined these energy levels, right? So the electrons were in these specific paths at exact distances from the nucleus. Okay, now we're saying, no, we can't specify where an electron is. We can just tell where it will most likely be. So when we say it's based on probability, we're saying it's where we can kind of say where electrons will most likely be found. Okay, we can't say it will be found there, it will most likely be found there. And this is where the term orbitals or electron clouds come from. Okay. When Bohr was defining his model, he defined them as orbits, right? Now we're looking at them as orbitals. So there's a big difference between orbits and orbitals, even though the names are pretty similar. With the Bohr model, orbits were specific paths, right? He defined them and said the electrons must be in these specific paths around the nucleus. They couldn't be in between. Now we know differently that actually we just define space, say the electron will most likely be within this region of space. Okay, that's what orbits are. I'm sure you've heard the term electron clouds before. So clouds are kind of like where these orbits come from. They're high probability regions where you'll most likely find the electrons. So where this was all coming from is we were just observing things that the Bohr model couldn't really define, or we couldn't really look at it using the Bohr model. So one of the things was photoelectric effect by Einstein. When you research Einstein, you find all kinds of stuff, right? Like he was responsible for a lot. Our focus is his work with the photoelectric effect. Okay, that's where he kind of played a role in atomic theory. With the photoelectric effect. What the photoelectric effect is it's just what he was noticing was that when light hits metal, when we have metal and you see and light is striking the metal, a stream of electrons will be ejected off the surface of the metal. Okay, that's what he was saying. And what this did is it kind of made us look at light having particle properties. Like we think of light as traveling through space in waves, right? That's just a form of energy traveling through space in waves. But if it can strike a surface and actually cause electrons to be ejected, we can kind of also think of light in terms of particle properties. That's where the term photon comes from. Like when we're looking at photons of light, they're just little packets of energy. So it kind of gives us the idea that light also has properties of particles, not just waves. Okay, because it's given off in these packets of energy, and certain energies will cause this to happen. It has to have a certain amount of energy in order to cause these electrons to be ejected off the surface. So I kind of like to think of the photoelectric effect as that carnival game where you have to throw like baseballs at the clowns on the shelves, right? And if you hit it with enough force, it knocks the clown completely off the shelf. If you don't hit it with enough force, it may just like push it backwards a little bit, or maybe knock it over, but not fall off the shelf. So you need a certain amount of energy in order to completely knock it off the shelf, right? It's kind of like the photons of light, the little packets of energy of light when it hits the metal. It has to have enough energy that it's going to be able to knock the electron completely off the atom. Okay. So if we kind of think of, like, here's our electron, right? And here's our photon of light coming at the electron. If it has enough energy, it's going to knock the electron right off the atom. Right off the metal. So that's photoelectric effect. Another way you can kind of envision that, do you ever see those, what they're called, those bulbs that have like spinning metal in there? One side is usually painted black and the other side is just the metal. Photometers. If you set it on your desk, as light hits it, it causes it to spin. Basically what's happening is the light is just hitting the metal side. Okay. And as the electrons are ejected off, it gives it a little bit of energy. It causes it to spin out of the direction. To be able to acquire to show you. I used to have one, but I think it fell off the shelf. that's basically the photoelectric effect. The reason we mentioned that is it was kind of like one of those things that got scientists thinking that we need to go a new direction to understand what's happening in electrons, that we can't really use the Bohr model. We can't really say that electrons just spin in these orbits or specific paths. We need more than that. We need more information. Another thing that came about was de Broglie. I think I missed somebody in between. With Heisenberg.
That wasn't in the presentation rubric, right? I didn't.
De Broglie?
No, I didn't see him in that list of people.
Maybe not. He's kind of like goes along with Schrodinger. They kind of like work off each other. So. But what de Broglie was noticing was that electrons, just like we just said that light has particle-like properties, I can kind of think of it as little packets of energy hitting something rather than one big long continuous wave. Electrons are so tiny, hardly of any mass at all, and they move so quickly that they actually move in wave-like patterns. So when we're describing their motion, this is where we get away from classical physics and quantum physics. They move in wave-like patterns. Okay, unlike when you throw a baseball doesn't go like this, right? In space, electrons, as they're zipping around, kind of move and have these wave-like patterns. So what de Broglie was noticing is they actually have wave-like properties as they move because they're so tiny, so light, they hardly have any mass, that electrons have these wave properties as they move. And we notice that light and electrons interact with each other, and this is why, because they both have properties, this dual wave particle property. So even though we know light moves through space in waves, it also is given off in little packets of energy. And electrons, being particles, are so tiny that when they move, they actually move in wave-like patterns. Okay. So that's what de Broglie was doing. I forget what his first name is. Louis de Broglie. His first name is Heisenberg, I guess I should say Werner Heisenberg. His name was Werner Heisenberg. So he was trying to kind of come off de Broglie's theory that electrons have these properties of both particles and waves. Okay. He gave us a Heisenberg uncertainty.
Why is the physics?
You can just say uncertainty.
I don't like this one. But I'll just become. You don't like this one.
Well, no, it's really called the uncertainty. People just refer to it as Heisenberg uncertainty. He didn't name it Heisenberg. But that's where this bumper sticker up here comes from. Heisenberg may have slept here. Did you ever tour a city and there's kind of like a plaque on a building or something that says so-and-so may have been here or something along those lines. Okay. Heisenberg's uncertainty principle
Who's uncertain whether or not he's
Is-
up there?
again, kind of referring back to this probability thing with the quantum model. What he stated was, we can't know both the position or location of an electron. Yeah, every time that door
That's someone's baby.
closes, it sounds like it's pretty loud.
That's someone's baby.
Feel a little double. So we can't know both the position or location, however you want to say that, position, location, means the same thing, of an electron. And its velocity. Simultaneously. Or at the same time, right? Simultaneously means at the same time. Can't know both the location of the electron and its velocity at the same time. Okay, what do we mean by velocity? What's the difference between speed and velocity?
Isn't velocity like how quickly it goes from this fast to this fast?
That's acceleration.
Oh, dang it.
But
Gotcha.
velocity is a part of that because you're looking at the change in velocity. That's what acceleration is. But what's the difference between speed and velocity?
Speed is how fast. Velocity is how quickly.
I don't
know.
But you're right, speed is how fast you're going. You can look at it in terms of force. It really gives us the direction. Like
Oh my
I can be
God.
driving 40 miles an hour, right? I can say I'm driving 40 miles an hour. Does anybody have in their car, like it tells you if you're going north or northwest?
Yes, yeah.
So that's telling me my velocity that I can say I'm going 40 miles per hour west, or I'm going 40 miles per hour east, right? Gives us a little bit more information. It puts direction with your speed. Right? It puts direction.
It sounds so much cooler than just.
Okay. But the part that we're focusing on, the reason I use velocity is we can't know where it's going. So imagine trying to play baseball or softball or volleyball or whatever. We rely on light reflecting off the ball to know where it's going. Right? So like you can line yourself up if there's a pop fly, you can kind of predict where it's going to come down if you're an outfielder that time you catch the ball. Right? Well, imagine if every photon of light that hit the ball changed its direction. Okay, so you'd be out here, oh, because every time the light hit it, it's changing direction. That's what happens with electrons. Electrons are so tiny that a photon of light is enough energy to deflect it. Okay, and again, that's where we're going away from classical physics to quantum physics, because with baseballs, that doesn't happen. Baseball is too massive that the amount of energy from the light hitting it doesn't affect it. Okay, it's too massive compared to that photon. With electrons, that's not the case. They're so tiny that every time a photon of light hits it, it changes direction. So we can know where it was when the photon hit it. We can detect, oh, the electron was there. When that photon of light hit the electron, it was there, but it changed its direction. Now I don't know where it is again until another photon of light happens to hit it, and I can detect it. So I can know where it was, but I don't know where it's going. Okay.
Does gravity affect?
Not as much as other particles, because they're so tiny that there isn't the force within the atom actually overpowers the gravity. As it's moving around, the attraction between the nucleus and the electron has more of an effect than gravity. So, because it's too low of mass. gravity is dependent upon mass. Okay, and then if we try to lower the energy, if we try to use a photon that has such low energy that it won't deflect the path, it's too low to be able to detect it. Like, we won't be able to know where the electron was anyway, because we won't be able to detect where that photon hit the electron. Too low energy. So that's Heisenberg's uncertainty. Just find that. Think of electron baseball or electron volleyball. Every time the light hits the ball, it shoots it off. So the person then that kind of put all this together and defined the quantum model was Schrödinger. I forget this person.
What's his first name?
Erwin. He was Erwin. It's Austria.
Oh.
That's why the two little dots are above the other. Erwin Schrödinger.
He's an old thing. He's Austrian. She knows that. I don't. He's an old thing. Hey. I need my shoulders stretched so bad. How do you want it stretched? Oh.
Okay, so he developed equations in the area of probability. So he defined or developed equations of probability telling us where electrons will most likely be found. Where electrons will most likely be found. So his equations would say, okay, 90% of the time you're going to find this electron in this region. Doesn't mean it can't hop out of there. Sort of like if you're looking for a teacher, where are you going to look first?
Their classroom.
The classroom, right? Because probably 90% of the day they're in the classroom. But is it possible that they might jump out of their orbital every once in a while and be somewhere else, right? They might be checking their mailbox in the office or running copies in the copier room. Or just
In the teacher's lounge,
going-
taking a nap.
Probably not, but that would be the least problem. Especially if you ever saw our teacher's lounge, if you ever see the furniture that's in there. It's like 1970s vintage furniture. So you could probably do some biology experiments. That's how long it's been around. How many people sat in this chair. All right, so he developed these wave equations that really define the quantum model. That's what we're going to go through. We're going to look at 4 quantum numbers, which are the results of these equations. And each of these quantum numbers kind of tells us where an electron is going to be in an atom. So you want to kind of think of it as like a map. Like we have the whole United States, right? If you're trying to find somebody and the first information you're given is they're in the United States. Okay. Is that going to really help you a lot? No, but at least it tells you what country they're in, right? So I know they're in the United States, I can start there. Okay, then what would we break it down? What would be the next piece of information if I want to know? The state that they're in, right? So you can pinpoint it a little bit further. It's still going to be hard to find them, but at least you got it narrowed down a little bit more, right? Then we can break the states down into counties and then maybe towns, right? So you keep kind of zoning in. That's how we're going to break this down with the quantum model. Okay, we're going to first define energy levels. Say, okay, the electrons here's the whole atom, right? That's like the United States. So then we'll break it down into states. Okay, so it's in here, there's energy levels. Then we'll break it down into sublevels. And then we'll take those sublevels and break them down into orbitals. Okay, and that's what the quantum numbers are going to define. So let's take a little break there. And you can, when the bell rings, you can kind of take. All right, so the quantum numbers now, like I said, we're not going to get into the mathematics or the formulas behind all this. We're just looking at what two Schrodinger's wave equations tell us about the atom and specifically where the electrons are and how they behave around it. All right. So there's 4 quantum numbers.
1, 2, 3, 4. Yes. That's correct. The surface of the Earth? Correct. Oh my God.
And we have the principal quantum number.
What, do they all have little symbols? No.
Letters, yeah,
They're just letters?
letters in terms of defining.
Like,
Hold on, I can.
Are they-
Straight edge.
what's the language?
English letters. Greek.
Latin? They're English
It's
letters?
Greek.
Oh my God.
Normally it's Greek letters.
I know, that's what I was like, it's little symbols like Greek letters. I
Nope,
remember.
Just letters.
That's why I was so it's boring.
All right, so the principal quantum number is usually represented with an n, and its possible values are positive, so n equals 1, n equals 2, n equals 3, and so on. And what this does is okay. So these are just distances from the nucleus. The difference between these energy levels and 4's energy levels, remember that 4 defined them as orbit-specific paths around the nucleus. This is just space, like from the nucleus to here is the first energy level. From there to here is the second energy level. So like if you're looking at a sphere, if this is your nucleus, and you want to think of this three-dimensionally, like spherically. This space here would be your first energy level. Okay. And if you get further away, this space here would be your second energy level, and so on. Does that make sense? So it includes all the space in between, whereas Bohr's model was the electron's going to be here, this specific path, or it's going to be here in this specific one. And so this is a cloud, yeah, it's more like clouds. Yep. So it's space. Energy level can contain up to 2n squared electrons. So every energy level can contain up to 2n squared electrons. So that means if you're in the first energy level, how many electrons could there be in the first energy level? So that's 1 squared
1,
times 2,
2.
2. So if you're in the first energy level, you can have up to 2 electrons. Remember, it's not, this isn't in parentheses. Okay, you're not squaring the 2. You square your energy level, and then take that times 2. So if you're in the 4th energy level,
30 kills.
4 squared is 16, 16 times 2. Make sense? All right, that's principal quantum number, simple enough, right?
And we're done for the day.
Now let's get a little bit more complicated.
No.
So remember I said it's kind of like taking a country, breaking it down to states. So now we're going to break the energy levels down into sub-levels. Break the energy levels down into sub-levels. And this is known as the angular momentum quantum number. These are on pages 107 to 109, by the way. And depending on references, that sometimes they name these a little bit differently. I'm just using the text. But I'm more concerned about knowing what they define, the action. This is represented with an L. And the possible values are 0, 1, 2, but it maxes out at n minus 1. Have a maximum value. You didn't have a maximum value. So your values can be 0, 1, 2, up to a possible maximum value of n minus 1. So you have to know what you're, with these quantum numbers, you have to look back at the previous quantum number to get your values for the next one. So you have to know what energy level you're in order to know what possible values. Okay, what this does is it breaks the energy levels down to the sub-levels. So it tells us basically how many sublevels it's going to break it down into. Because remember, the energy levels are going to get bigger as you get further from the nucleus, right? Because if your nucleus is here, and we're talking about spheres, okay, closer to the nucleus, you have a smaller sphere, right? As you get further away from the nucleus, you have bigger spheres. So there's more space in there. So it makes sense that you'll have more sublevels in higher energy levels. Sort of like in bigger states, you have more counties and cities, right? It's bigger states than what you do in smaller states, right? There's more space. Right? So if your sublevel value is 0, we call it an S sublevel that has spherically shaped. If your L value is 1, we call it a P sublevel.
Yeah, would that be?
And I'm just using words that start with that letter. It's not how they came up with. But they kind of look like peanut shaped because they have 2 lobes, like a peanut, normal peanut has like 2 lobes. And those lobes are kind of like the cloud region where you like we talked about. So this is a spirally shaped cloud. This is a cloud that kind of has two lobes on it. Does that make sense?
Yeah. Sorry.
If L equals 2, it's a D sublevel.
Diamond.
Diagonal.
Kind of like
Diagonal.
two peanuts laying across from each other. You have 4 lobes.
That's super fun.
Is that one oral? Because on the other one, it's like wrong, or this one is that one, or this one.
She really thought she did something.
I didn't get it.
Triple peanut. TP.
Oh my god, is it F?
F sublevel.
4. Flower. Flowers in that thing.
And I will be showing you like a video clip that kind of shows these 3-dimensionally because I are wrong.
I
Wait,
believe,
but
I believe
how many
you.
petals does the flower have?
Probably 8.
That's a lot.
How many?
Maybe like 8. So like, I'll give you a little bit of my argument. So S would be spherically, right?
Looks like a ball. Looks like a billiard ball. to me.
Is anyone here drawing dollars?
So P being peanut, I like 2 clouds, 2 little T clouds. Okay. Double peanut would be kind of like that. But then another one this way.
Ooh, interesting.
And flowers.
Like a quadruple peanut.
Okay. That's the best thing.
Oh,
I'll
wow.
show you a video.
I want to try making it.
Yeah. Let Cassie do it.
Can I try?
She should be done doing the artwork. Artwork first. Yeah,
Then
it's
maybe
just not
not.
just artwork. is stupid. I don't like it. Okay. Okay. I think I could do better. Can I try?
Or you just go like this.
All right. I think everybody gets it.
Beautiful.
Alrighty.
That's what makes it.
So
Bravo.
you can have up to n sublevels per up to n sublevels per. And I say up to because that just means that there's that much space for them, right? Doesn't mean that you'll always have it fully occupied, but there's space for that. Sort of like in a hotel will have a maximum occupancy, right? But rarely is the hotel going to reach its maximum occupancy because sometimes you might have some rooms that aren't being used, or they might be used by one person, but could hold 4, right? So it's just the maximum amount that you can have. Doesn't mean that it'll be fully occupied. Does that make sense?
No.
That's the angular momentum. So we got energy levels broken down into sublevels. I'm just going to erase this half before here.
Break the
Sorry.
flower.
Yeah, what the heck? It's never ending. It's literally just.
So the third quantum number
Not funny.
What did you ask?
I didn't. That was a sneeze.
and it's represented with an M subscript of L, ML. Okay, an M with a subscript of L. M sub L.
Like love.
And its values start at negative L up to a maximum value of positive L, being all integers. So your range is from negative L, from this. Remember I said you always have to look back to the previous quantum number to define the next one. So your value range goes from negative L to positive L, only integers. What this does is it tells us how many orbitals there are going to be in each sublevel. And defines their orientation about the nucleus, like how they line up around.
What?
So if I'm in an S sublevel where my L value is 0, how many values am I going to have for my M?
Zero?
Just one value of 0, right? One value of 0.
That's fine.
That means in any S sublevel, you can only have one orbital. But this kind of makes sense because what shape did we say S orbitals are?
Spherical.
Spherical. So if I turn a sphere, does it look any different? Is it so it only has one orientation, right? It only has one orientation, but I can turn a sphere any way I want to and it still looks the same, right? It's not oriented differently. So if I, like a basketball, if I'm holding a basketball and I turn it around, it still looks the same. There's not more than one orientation that I can do. Okay. So in any S sublevel, you can only have one orbital. If we go to a P sublevel where L equals 1, now what are my possible values for ML? It goes from
-1.
negative to positive, right? So -1, and they're integers, right? So what's my next integer after -1? 0. And 1 is my maximum value, right? Because it goes up to a maximum of L, which is 1. So I have 3 orbitals
Like
in a P sublevel.
A pizza level? Oh, you said pizza.
P sublevel. And that makes sense because I can lay my peanut sideways, or I can put my peanut up and down, or I can put my peanut sticking behind the board or out towards you, right? So there's 3 different orientations of the P orbitals. We call them PX, PY, PZ. for the three axes, the x-axis, y-axis, and z-axis. Because you could lay the peanut along the x-axis, along the y-axis, or along the z-axis.
These make the one that like.
It's three-dimensional, so like here's x, y, and then z would come out this way. Okay. So you'd have one of your, this would be your px, right? This would be your py. And then you'd have a pz come out this way. I'll just kind of draw it the best I can.
Do it side.
That's like, it's supposed to be looking like it's sticking out or behind. the
And
word.
just like a football.
Right, so all of them put together kind of make a sphere, right? Fills up that. E sublevel. That's where L equals 2, right? So my ML values. What's my range? I'm going to start at what? -2.
1, 2.
What comes after -2?
Take one.
Then,
Zero.
then
1. Oh. Then 2.
because it goes up to a maximum value of 2, right? The maximum value is L. So how many orbitals are there? 5.
She's munching. Sorry.
So I'm not going to attempt to draw those, but basically you just have these double peanuts turning different directions, right?
Double peanuts. Double peanuts.
That's sublevel. What are my possible values there for my F sublevel, for my orbitals?
-3, -2, -1, 0, 1, 3.
Right, again, you're going to start at negative L to positive L, right? So -3 to +3.
Oh, okay.
How many orbitals is that?
7.
Okay, speedy. One bacon now.
Right. Now, even though I stopped at F, there are G orbital or G sublevels, H sublevels, and so on. But we're not going to get to them because the current atoms that we know of, the current elements, we never have electrons occupying a sublevel above the F sublevel, unless the atom's excited and it jumps into higher energy levels.
Okay.
Okay, but in the ground state, we're going to focus on ground state. In the ground state, none of our elements will have electrons beyond an F sublevel. So there are G sublevels and H sublevels. But we're just stopping that. You get the idea.
Take a little bit.
Okay? So that's 3 of the 4 quantum numbers down. The 4th one's pretty easy though.
Okay, it's D.
The 4th quantum number is the spin quantum.
Oh, the spin. Eddie goes to
I love this shit. I love spin.
just have it demonstrate. Guys, for next time, we understand.
And that's M sub S. M with a subscript of S. So-
MS.
And there's only 2 possible values.
Zero.
-1 and 1. Oh, -1/2.
-1/2 and +1/2.
You.
Okay.
Sorry.
And just like the name says, it's just telling us which direction the electron spins as they move around. So electrons don't just move around, they spin as they're moving, sort of like the Earth, right, or the planets spin as they go around the sun, right? It's the same thing. They're just spinning very rapidly one direction or the other. And because of that spin, it gives them magnetic poles, just like the Earth has the North Pole and the South Pole. Electrons have 2 poles on them. They have a positive pole and a negative pole, depending on which way they're spinning. So if an electron is spinning one direction,
What?
okay, if it's spinning one direction, it gives it a positive and a negative pole, right? If it's spinning the opposite direction, the poles will just change. So if it's spinning this way,
Let me shake it off. Hold on. I see actually two.
the poles would actually just switch. Does that make sense?
Yeah.
So if it's spinning one direction, I don't know which is which. I'm just giving you the idea that there's the poles switch directions when the electrons are spinning opposite.
Oh, yeah.
Can you go up there? Can you
And
go
just to
up
kind of jump ahead a little bit, what this allows, this is what allows two electrons to occupy an orbit. Oh, I forgot to put that.
Sorry.
I forgot to put that up here, up to 2 electrons per orbit. Up to 2 electrons per orbit. Okay, and the reason for that is electrons are both, if 2 electrons are in the same orbital, right? If 2 electrons are in the same orbital, they're both negatively charged, right? They both have an electrical negative charge. What do 2 negatives do to each other?
Cancel each other. Deflect.
They repel each other, right? So in order for 2 electrons to be able to be in the same orbital, they have to be able to spin opposite directions. Because if they spin, listen up, if they spin opposite directions, then their magnetic poles are opposite of each other. So that magnetic attraction cancels out the electrical repulsions, okay? And that's what allows them to occupy the same orbital, that same space. Because if they didn't have this magnetic attraction, the electrical charges would repel each other and they wouldn't want to be in the same orbital, right? So since they have this magnetic attraction, it allows them to occupy that space together because the magnetic attraction cancels out the electrical repulsion.
Okay. Is that okay?
Wait.
All right, so magnetic attraction cancels out electrical repulsion.
That's smart.
That makes sense?
All right.
Because electrically, they're going to repel each other, but if they're spinning opposite directions, the magnetic poles will attract each other. So that allows them to be.
Take your word for it.
Happy day.
Happy day, happy day.
We're gonna do helicopter.
So I didn't actually write out the definition there, but the spin quantum number just tells us the direction that the electrons spin. The direction of the electrons.
I'm like, she doesn't make it. That's funny. Okay.
Get that off my head. You need therapy.
So you can kind of think direction of spin as being clockwise, counterclockwise, or you can think of it as forward tumbles, backward tumbles.
Georgia can do both of those. Yes.
I cannot,
That's really bad.
nor will I try.
I'm doing helicopter. Come on. You know, you have to go slow.
I know you're sad that there's only 4 quantum. We'll do more with it. They will now define our electron configuration. Tell us our electron.
Why? Why is it going so slow?